Okay, so now that we have discussed the Cartesian and the polar case, let's talk about the general case. And by that I just mean that you're using arbitrary coordinates, not necessarily Cartesian coordinates or polar coordinates. So maybe before giving you the formula, let me just give you some examples of what I mean. So you could think that maybe you're defining two new coordinates. Instead of calling them r and theta, you just call them u and v in general. So you could say that you're using two coordinates u and v, such that x is u squared minus v squared and y equals u times v. Okay? And so here you think of u and v as new coordinates. And the point is that we don't necessarily know what these coordinates mean. So for example, when you use r and theta, it's clear that r is like the distance from to the origin, and theta is just like the angle of inclination. But here it's like, I haven't given you any particular interpretation for what u and v are supposed to be. And you should not necessarily think that there's like a straightforward interpretation of them. In fact, it's complicated in general to just understand what the meaning of the new coordinates are, what the meaning is. So this, for example, could be a possibility. One, I'll actually show you some animations at the end of the video, so it won't be that bad. So this is like option 1. Option 2 would be to say that x equals v times e to the u, and y equals v times e to the negative u. And again, it's not obvious what these two coordinates u and v mean. They do not have they will not have the same meaning as in here. Okay. Now in this particular case, you can actually say a couple more things. Why is that? What if you take x times x times y? Notice that x times y, right? That's well, when you multiply this times this, e to the u times e to the negative u just goes away, because you get v squared, right? Like these two exponentials cancel each other out, so you just get v squared. And in particular, this tells you that you can use this equation to solve for v. And so if you wanted, you could say like that v equals square root of x times y. And likewise, if you say were to divide x over y, then this gives you this, and then if you take ln on both sides, you get ln of x over y equals 2u, and you can again use this to solve for u, and say that u equals 1/2 ln of x over y. So the reason why I'm doing this is that sometimes if you have x and y in terms of v and u, then it's easy to reverse a process and write v and u in terms of x and y. This is analogous to somehow you can write when we wrote like r and theta in terms of x and y in the case of polar coordinates. But actually, if you try this out here, you'll see that it's not okay. This froze for a moment. I was just saying that it's not easy to write u and v as functions of x and y here. And so what I'm about to do is just show you a couple of animations so that you see how the curves of constant u and v look like here. when you try to draw them on the xy plane. This is the analog of trying to draw the curves of constant r and theta in the case of polar coordinates. So for example, this was one possibility, this was another possibility. Option 3 that you could write would be x equals u cosine of v, and y equals u sine of v. And or let me, well, I'll write it. It's actually, it doesn't matter which one you call v and if you do this, like if you write x and y in terms of u and v in this way, you should realize that this is secretly polar coordinates where v is playing the role of r and u is playing the role of theta. So sometimes you might run into coordinates that you know from before. It's just that maybe you don't recognize them as such because their names were changed. So the next animation will show you like the difference between these different coordinates and like what their effects are on the xy plane. Let me show you an animation illustrating the different coordinates, how they look like on the xy plane, and how would they look like if you made a different plane where one of the axes is the u axis and the other axis is the v axis. So this is called the uv plane in general. Okay, so for the first transformation, we're just going to take x to be v cosine of u and y to be v sine of u, and notice that that's exactly the same transformation as for the one for polar coordinates, where v is playing the role of r and u is playing the role of theta. So you should think of this as the theta axis and this as the r axis. Okay, and so we have this rectangle on the uv plane, which is really the the theta r plane, and we want to see how this looks like on the xy plane. So if I take this point here and I start moving it around, let's say I move it around along this segment. So I'm going to move it in this segment where v, the height, is constant. But remember that v is like r. So I'm going to be moving in such a way that r is constant. And when you move with constant r, you're moving in a circle. So really what's increasing is the horizontal coordinate, which is u, which is really theta. So the angle is going to be increasing. So we start with an angle which is very close to 0, so it's almost next to the x-axis, and that's going to be increasing until, well, remember the 2 pi is like 620 something. So this is going to do more or less like a complete revolution. So let's see what happens. So you should see on the right hand side, as the particle moves, right, the green particle moves, the yellow particle moves as well. Oh, okay, sorry. Sorry about that. So as the green particle moves, the yellow particle moves. Is that you have to go slowly so that it traces everything out without issues. But again, this is moving with constant r. So this straight line on the uv plane actually becomes a circle on the xy plane. So one way to think about it is that somehow when you make changes of coordinates, like it's like putting like some glasses that distort the image. So under polar coordinates, if you draw an axis to be r and another axis to be theta, then basically the circle is distorted so that it becomes a horizontal segment. Okay, now let's say that I'm going to move through this segment now. So what's this segment? Well, in this segment, u is constant, but again, u is like theta, so the angle is constant, so you're going to be moving at a constant angle, and that's precisely a ray. Okay, so now r is the variable that's going to be decreasing. So this is what's happening now. So we are located at this point. I'm going to be moving at a constant angle, and I'm going to be shrinking r. So this particle is now going to be moving towards the origin. Which is what you see here. So you see constant values of, so here vertical segments, like if you take a ray under your UV glasses, the ray becomes a vertical segment, and a circle under the UV glasses becomes a horizontal segment. So this is how this looks like in the case of polar coordinates. Here's the other transformations that I mentioned in the video. So now x equals v times e to the u, and y equals v times e to the negative u. I'll show you how to work this out later, but the idea is, like, say horizontal lines now look like hyperbolas, okay, and on the other hand vertical lines actually look like straight lines that pass through the origin. So vertical lines look like straight lines through the origin, and again horizontal lines look like hyperbolas, okay, and again vertical lines look like straight lines through the origin. This one is very vertical, so if you want one that's less vertical, you can just move this around a little bit, and then you get another different straight line through the origin. So you see, you start getting let's put the animation. You start getting these regions, and that's the point of hyperbolic coordinates. This is the other change of coordinates that I mentioned in the video: x equals u squared minus v squared, and y equals u times v. And here again, this one is a bit harder to figure out maybe what's going on. So let me just show you the animation. We're going to go around a square, and you'll see what the square gets mapped to. So you end up having this distorted parallelogram, if you want to call it something. And like, these curves are actually, I mean, harder to identify. Let me show you something else. So these are the same transformations from before, and so the square, that like a square from the previous animation, like basically looks like a figure like this. And so the idea is like an area, if you just like say, like this square has area 0.04, okay, but this distorted square has a different area 0.1184. So you need to multiply by a rescaling factor that will make sure that the areas match up correctly, and that's what the Jacobian is supposed to do. So basically the Jacobian will be like a rescaling factor that compensates for this distortion that we are looking at. So you see, like if you move these blue squares, the blue squares on the UV plane always have the same area, but their transformed versions have different areas, and so the Jacobian takes care of transforming the areas so in such a way that that rescaling the areas so that they match up in the end. So as you saw from the animation, what happens when you have a coordinate system, when you're using a system of coordinates which are u and v, what you end up getting are curves, right? Curves of constant u, or curves where u is constant. Okay, so let's say like they look like this. So here u constant, and you also get curves where v is constant, which may look like this. So here v is constant. Okay, and like the point is that you should not think that in general we know how they look. So that's why they are called sometimes just like curvilinear coordinate systems, because their curves are not obvious. It's not obvious how they look like, but still they sort of break down the xy plane into pieces. And so you may want to know what the formula for the area of one of these pieces should be. Okay, so let's try to talk this out. And like again, it's essentially the same that we discussed before for the case of polar coordinates or Cartesian coordinates. So say I choose a point here, which is represented by values u naught, x, v naught, which is like similar to r naught, theta naught before. Like it's just some fixed value of the value for u and v. Okay, and so if you think of this curve where u is constant, right? Remember that this curve had u constant. So along all the points here, the value of u is u naught. Okay. I should put it like, I'll put it like this. Like you took a point x naught, y naught. Maybe this is a better way of saying it. Where u is constant. So any other point here, x comma y, will be of the form. What you should think is like this should be of the form. Let me put it. Sorry, need more space. Here's a point. Any other arbitrary point is of the form x of u naught comma b y of u naught comma b. Well, what I mean by this notation is that x and y are being written out explicitly as functions of u and v, but we know that the value of u has been fixed to be equal to some value u naught. So this is why it looks like this. And so you get a curve which only depends on v, right? Because if u is constant, the only way to get this curve is by varying the values of v. So the point is that there's like a tangent vector here, a velocity vector, and this velocity vector is the same as a partial derivative, as the derivative of r with respect to v. But really what we're doing here is like taking a partial derivative, because we're taking a derivative when only v is allowed to change. So if you want to drop these knots, this awkward notation, you can just say that this vector, this yellow vector, is a partial derivative of r with respect to v. Okay? And the point is that something similar is happening here. Now here v is constant. So that means that if you take a point on this curve, right? If you take a point on this curve, v is constant. So x is only changing because u is changing. So you put here x of u v naught, y of u v naught. meaning that only u is changing here. So this is like a position vector in terms of u. And again, there's a, in this case, there's a tangent vector. Let me use a different color. There's a tangent vector, which is, again, what you would take by differentiating this with respect to u. So this is like what you get by changing just u, holding b not constant. So that's essentially like a partial derivative with respect to u. So to maybe draw the picture more clearly again, what I'm saying is that, let me zoom in so that it's clear what the situation is like. What I'm saying is that if you take a point here and you're trying to find the area of this piece, then you can move, you have a velocity vector along this curve, which is, well, it's tangent, so maybe we should try to do it more tangential. So you have a velocity vector along this curve, which is the partial derivative of the position vector with respect to v. And you also have a different velocity vector along the other curve, which is also tangent here. So it's just a partial derivative of the position vector with respect to u. Okay? And again, the point is that the displacement is like velocity times time. So here you get a displacement by, you get this bigger vector, this displacement vector, which is just the original one, by the amount of time that you moved, which in this case is delta v. Okay? And you get another displacement vector here, which is, the time here is now delta u. Okay? Now, contrary to the case of polar coordinates or Cartesian coordinates, these two vectors need not be perpendicular to each other. So really what you should think here is that you have more of a parallelogram rather than a rectangle. So again, this is like the vector, the dr du times delta u, and this is the vector, sorry, this is a, yeah, this is the vector dr dv times delta v. Okay? And so the area, like we don't know like a formula for this area of this curvy shape, but we do know the area of a parallelogram, right? In fact, the area of a parallelogram, remember, is the cross product of the norm of the cross product of the vectors. So it would be the norm of the cross product of these vectors, which is, I mean, since it's a norm, it doesn't matter in which order you take them, so let me put it this way. But now, this delta u, delta v, they're like scalars, they're just numbers. You can take scalars outside a norm or or a cross product. So really, you get this. And this quantity is what people call the Jacobian. Okay? So in the next video, what I'll do, and like the idea is that this area of the parallelogram is a better approximation for this other area as you start shrinking down the delta u's and delta v's, like the amount of time that you moved in a certain direction. Okay, so what I will do next video is just give you the black box of how we're going to use the Jacobian, and then we'll do 2 examples so that you get like the idea behind it. In fact, maybe to make it even more of a black box in the next video, let me just write this down a little bit more concretely. So that the formula I can just write next time immediately. So you should think of a point, the position vector of a point here, r, x, comma, y, as secretly being in 3 dimensions, so that you think of it as this being the z-axis pointing towards you. So that way we can compute this cross product. So the partial derivative of r with respect to u is the partial derivative of x with respect to u, the partial derivative of x of y with respect to u, comma 0. And the partial and the partial derivative of r with respect to v is a partial derivative of x with respect to v, partial derivative of y with respect to v, comma 0. Okay, so we're going to take the cross product between these 2 vectors. So the Jacobian let me check what notation I want to use for the Jacobian. So the Jacobian is just going to be, I guess we'll include this with absolute values. You may not include the absolute values already, like the norm. Well, I guess, yeah, let's include the norm already. So this will sometimes be noted like this. It's just this norm so it's the norm of that vector, which is this cross product. So remember, it would be the norm. Remember the trick for computing a cross product. And let me switch notations to make this more easy to follow. Remember, this was the alternative notation for partial derivatives. So the Jacobian is this cross product is easy to compute because it just gives you 0, 0, xu yv minus xv yu. Okay, and so it's the norm of this vector is just this absolute value. And this, if you don't want to think of it as a as a cross product, you can just think also as the absolute value of the determinant of some matrix. And this is a matrix whose entries are say q. Let's see. Yeah, like you can write it like this determinant. So it's like the determinant of partial derivatives, the partial derivative of the position vector with respect to u, and the partial derivative of the position vector with respect to v. So there are many alternative ways to write this formula. So what I'm going to do next time is just give you the way to write it down as a black box, and then we can start using it for examples.